Hello, this is Jin Guo Lin from Department of Physics, Harvard University. Today, I want to introduce reversible computing and reversible programming. It will cover three parts. In the first part, I will introduce a bit about reversible computing. In the second part, I introduce reversible programming using the reversible embedded domain-specific language ELAN. In the third part, I want to introduce the automatic differentiation in ELAN. Let's start from our physical world. There are a lot of phenomena. Some are known as reversible, like the gravity and electromagnetic forces. Some are known as irreversible, like the friction. The fact is all these phenomena in the universe can be explained by a reversible quantum dynamics. Then how come our program style is irreversible? Our program is irreversible in different ways. For example, in error handling, in assignment, in function return. Error handling will clear your program space. Assignment will clear the information in a variable, while the function return will redirect you to another place, and when you run backward, you don't have the information to run the original branch. So here, we define the information as another word of the uncertainty. It is quantified by the information entropy. And information erasure means the decrease of information entropy. It makes the system in a more certain state. The result of information erasure is it requires dissipating heat to the environment. I show this by introducing Feynman's thought experiment in his book. Here, assume we have a collection of boxes, each containing a particle inside. It can be in the left side or the right side. We compress the piston, which is attached to the box. We compress the box to half of its size. In the first case, we consider we know nothing about the position of the atoms. So the system can be viewed as an ideal gas. We compress it to the half of its size. We need to do work because our piston hits the particle and accelerates it. However, the particle energy keeps unchanged because we further assume this process is isothermal. So this part of energy is dissipated to the heat bath. In the second case, we consider we know one bit information about each box. We use Boolean number 1 to denote the atom is in the right half. We use Boolean number 0 to denote the atom is in the left half. If the box state is in 1, we compress the piston from the left. If it is in state 0, we compress it from the right. So that we need to do zero work because our piston never hits and accelerates the particle. Here we come to a very important conjecture called the Landau's principle that erasing each bit information comes along with kT log 2 heat dissipation. We can see this point by relating to these two cases. In case 1, the original information system is more uncertain. By pushing the piston, we make it into a certain state. In case 2, the original state, since we have knowledge about the original state, the original system is in a certain state. It has no information. Hence, we erase information in the first case, but do not erase information in the second case. Later, people proved Landau's principle rigorously from quantum dynamics. Here, we summarize the first part a bit. We show an isolated system must be reversible, and our program are not reversible. As a result, we need a heat bath, and each irreversible statement requires dissipating some heat to the environment. Its lower bound is kT log 2 over per bit, called the Landau's principle. There is a more detailed discussion in this interesting YouTube video about the energy efficiency of reversible computing devices. In this second part, I will use the reversible embedded domain-specific language inline as an example to show how does a reversible program work. Inline's main feature is contained in a single macro at I. When you use this macro to define a function, it gives you two functions, the function itself and its inverse. The function returns the input arguments automatically for you. So when you define an identity mapping, you do not need to write anything. The second feature is every instruction is reversible, and every object is mutable. One can write a reversible program with a general design pattern that writing the program in an accumulative style. For example here, in order to compute the exponentiation of x1, instead of writing x2 equals to xbx1, we use x2 plus equal exbx1 instead. There are also swap-like primitive functions defined, and one can use previously defined reversible function in another reversible function. Here I want to emphasize, even though the complex number is not reversible, we can change its fields directly. This is because we compiled this program in such a style that when you compute the output, we analyze this statement and assign a new complex number to its original variable. The third feature is one can write reversible control flows. For example, here is a reversible if statement. There are two conditions in a reversible if statement, the precondition and postcondition. Its inverse is exchanging precondition and postcondition, and inverse its statement. In the forward computing, the program only checks the precondition and a specific branch. The postcondition is to check the consistency between the branch you entered and the value of post condition. Otherwise, an invertibility error will be thrown. Here is an example when postcondition is required. In inline, if you do not input a postcondition, it will copy the precondition and use it as the postcondition. But sometimes this does not work. For example, here, in order to compute the absolute value of x, when we enter the branch x smaller than 0, we flip its sign, and the postcondition does not consistent with the branch that you entered, so it will throw an error. Instead, you should write something like this. You should use another Boolean variable to keep the information of x. When we flip the sign of x, we also flip the value of this sign. So we can define this function correctly, and a reversible while statement can be defined in a similar style. It is actually a from while condition. It also contains two conditions. One is from condition, another is while condition. In forward computing, the program only checks the condition 2, the while condition. The from condition is only to check consistency. It is initially true and later becomes false. Its inverse is exchanging two conditions, and the inverse is statement, and the condition expression should also be inverse. We use a Fibonacci example to show how this works, how to use it. In this example, we can, because there is a counter variable, which is initialized to n, so we can use it as a from condition, because it will later be changed to a value not equal to n. And the while condition, Yes, this counter is greater than 1, it will be used to control as a break condition of this while statement. We can check the correctness. The reversible while for statement is relatively simple. We just exchange the start and stop and flip the sign of step. The first feature is reversible memory management. We can use left arrow to borrow some zeros from a system and use the right arrow to return some zero to a system. The program will assert that the allocated variable is equivalent to the variable on the right hand side. The alignment target can also be a dictionary. For example, here we implement a complex valued log to show how to deallocate correctly by erasing the value to 0. Naively, if you do not use memory management, you would require 4 input arguments. Y is the output, X is the input, and 2 intermediate variables. This kind of interface is really cumbersome to use. Instead, we can write this function in such a style that it contains only 2 arguments. We borrow 2 variables from the working tape and compute the results on working tape. In the copy phase, we copy the results to the output variable. And in the uncomputing phase, we undo the computing process and return the value of n square n to the system. There is an even nicer way of writing this in ELAN. One can use the @routine macro to annotate a computing process. When you need to uncompute this code block, just insert an tired @routine at the correct place. Here we also use a macro @zeros to allocate multiple zeros. Use the check-off macro to turn off the invertibility check to improve the performance, and an inline macro. Great, now we have a brief understanding of what is a reversible programming language. In the following, I am going to introduce the automatic differentiation in ELAN. To understand the automatic differentiation in ELAN, we need to know the difference of 2 types of automatic differentiation. One is tensor level automatic differentiation, and another is scalar level automatic differentiation. For example, to implement the backward rule for matrix vector multiplication, in tensor level, we derive the backward rules manually for tensor operations, while in scalar level automatic differentiation, we decompose tensor functions to scalar functions. For example, here we decompose matrix vector multiplication into multiplication and addition on scalar. Implementing AD on scalar have the advantage of having very limited number of primitive functions, but it also suffers from several drawbacks. One is hard to utilize BLAS because it does not know it is computing a BLAS function, and another is it is harder to manage the memory caching on scalar. ELAN's AD is most similar to the forward automatic differentiation package in Julia. Forward diff and reverse diff are very different. They use chain rule in a different way. For example, here we have a mapping from input parameter P to output parameter Q, where we have an intermediate step of computing y equals to fx, and it has an inverse operation. The forward computing does not require the inverse computing exist, and it propagates the Jacobian in the same direction as the program computing process. It multiplies the local Jacobian on the left-hand side to the gradient vector and update this gradient vector. This gradient vector is about multiple outputs with respect to a single input. While in the reverse mode automatic differentiation, we propagate the gradient in the inverse direction as the program computing. We multiply the local Jacobian on the right hand side and update the gradient of single output with respect to multiple inputs. In forward diff, there is a number type called dual. It wraps a real number with a gradient field. When computing with this dual number type, for example here, the sum function also updates the gradient field. In reverse mode automatic differentiation in Nilan, we also have a similar type defined, which is a jiva. We wrap a number with a jiva type and do the inverse computing. Here I want to differentiate the accumulative sign function. Its inverse function is minus sign. We insert the jiva type to this inverse function, and we can get the input gradient. We can check they are equal. Here I use an example of computing complex valued log to show how to compute the gradient in Nilan. Here I accumulate the real part of the C-log function output to the loss. Nilan computes the gradient in the following style. We first compute the forward pass to get the output. Then we wrap the output with gradient, where the loss function has a non-zero gradient field, which is 1. And we insert this new element to the inverse function, and we get the input. This input carries gradient. In the forward diff, we wrap the inputs directly with a dual type. The number we want to differentiate, we put a 1 at its gradient field. We do the forward computing, and the output carries the gradient. And we can check they are similar, they are equal. There is a shortcut to compute gradients in Nilan, which is the gradient function. The first argument is the function name. Second argument is the function input. There is also a keyword argument, a loss. It specifies which argument is the loss. There is no free lunch. Nilan can handle instruction level reversible computing flexibly, but also have significant overheads in either time or space. In the following, I'm going to use two cases to study the overhead in reversible computing to differentiate the program. The first case is differentiating a linear program, for example, an ordinary differential equation solver. At each step, the program computes a new state. In regular computing, this state is deallocated immediately. We use the white circle to represent a state deallocated here, and its accumulative version in a reversible style needs to generate a new state in each step, and this state cannot be deallocated immediately. So in such a way, it is not too different with traditional programming. However, it allows uncomputing some states using the compute, copy, and uncompute process. And this compute, copy, uncompute can be applied recursively at a different level. For example, you can use a coarser-grained compute, copy, uncompute. By recursively applying this algorithm, we can find the optimal solution to compute a long program in limited time with minimum space. And this solution corresponds to the solution of the Pebble game, and we do not have time to talk about this game, but one can search this keyword. The optimal space complexity has logarithmic overhead with respect to time or the number of computing steps, and time complexity overhead is polynomial. So here we do a small numerical experiment. We suppose we want to compute a 10,000 long linear program, and the compute copy and compute hyperparameter k equals 2, which means compute 2 steps and one step back. And then recursively apply this algorithm will give you need to cache only 16 states. The peak memory is 16, while the time overhead is 148, which is quite a lot. However, we can use a different case. Like here, the peak memory usage becomes 51. The time overhead becomes acceptable. It's only about 6 times. And okay, well, how does it compare with the famous optimal checkpointing algorithm for a linear program that's proposed by Guo Lin? It is also a recursive algorithm that checkpoints take the checkpoints of program cleverly, and Guo Lin proved that both the time and space complexity the overhead can be logarithmic. Here we also run do a 10,000 step simulation that we have only 2 checkpoints, and the peak memory usage is 3, and the function call overhead is 93. And if we increase the number of checkpoints, we can see the peak memory usage increased while the number of function call is only 4-fold. It's more efficient than the Bennett time-space trade-off scheme. We show the plot here where the solid curve is Bennett's algorithm and transverse is dashed curves. Transverse is more efficient. So what's reversible programming good at is actually not differentiating a linear program. It's about the flexibility to utilize the reversibility and to compute intermediate results under control. Here we in the following I show a second case of differentiating linear algebra function, where we implement the Hausdorff QR, which is an algorithm in Julia standard library. But I'm not going to introduce the detail of the implementation because it's very long, and we just show the comparison with manual differentiation. First, it is slower. This is because manual AD is very fast. It only contains matrix multiplication. And another drawback is there is an additional space overhead that's proportional same size of the input matrix. It is actually acceptable. We only have an additional copy of the input matrix as a space overhead. And there are also advantages. One is it is instruction level automatic differentiation is stabler. This is because it can handle rank deficient matrices. It is actually I did not expect this to be true, but it turns out to be true. The rank deficient matrix can be handled very perfectly. Well, also for the complex numbers. Here we show the performance by using the benchmark. This is a generic implementation of QI decomposition in Julia standard library. We check the performance, and it takes 7 milliseconds to compute the 200 by 200 matrix. Well, its reversible counterpart is about 1/4 slower than the original program, and if we want to differentiate this QI decomposition, we need to compute the 1 forward pass and 1 backward pass, which we can see the overhead, the computing time is 4 times the pure forward reversible computing. These are the take-home message. You can find this notebook here.